This is Jeremy Kleininga, Charles Berg, and Kevin Kingma. Our project was a thermal control system and experiments heat transfer and control system classes to run on this system. I will start with the purpose of our project. We felt lab time and lab work would greatly increase students' understanding of heat transfer and control system concepts. Control systems especially is a conceptually difficult class, particularly for students with a mechanical emphasis. Also, we thought that increasing the amount of time that students spent on different controllers, such as proportional, integral, and derivative, would be a great benefit and help them understand the behavior and advantages of the different types. We thought the best way to provide a solution for all of these goals would be a piece of lab equipment that would allow students to work with different heat transfer, control systems, and controller concepts. This is a schematic of our original project design. In this design, fluid flows through a tank in which it is heated and stirred to provide a uniform temperature. The goal was to provide a system where students adjust the heater output to provide a uniform temperature for the water leaving the tank. However, there were several problems with this system, as Charles will discuss.
There were a number of issues that led us to abandon this original idea of ours. First, having flow through the system caused a lot of complexity with the mathematical model. And steadiness in the flow and the temperature of the water entering the system would necessitate very complex controls. We said that a system like this would be too complex for the target audience, the students that this system would serve. So they wouldn't end up learning anything, they just end up watching the system and wouldn't be able to analyze it and learn anything from it. This design was also a waste of water and required a very expensive heater. For our final design, we decided on constant volume of water with a pump to keep the water well stirred to keep the temperature even throughout. This system was a lot easier to model mathematically and allows for more accurate measurements. It was also better at displaying the types of behavior that students could understand and analyze in the lab. It also includes a lab interface. Next, Jeremy will discuss the heat transfer side of the design.
This system is transferred out primarily by convection of heat from the container wall to the air. To approximate the rate of heat loss, the heat transfer coefficient is being found. This coefficient is based on the properties of the surrounding air and the shape of the container. The container shape is important because it influences how the air moves around. Since a container can be placed horizontal or vertical in still or moving air, 4 different coefficients needed to be found. Each coefficient was found with equations specific to each case. Heat loss is then found by multiplying the total coefficient by the container surface area and the difference in temperature between the container wall and the air. Heat loss values that we found are approximate because the actual behavior of air is hard to predict. Now Ryan will describe the control system we used.
The second design aspect of our project was a control system model for the system. For our system, there was 2 possible ways to model the system. The first, as shown here, is a first order system. In this system, the heater was regarded as heating instantaneously or the time being negligible. Therefore, the time of fastest rise in temperature is right at the beginning, where there is the greatest difference in the water temperature and the heater temperature. However, if you assume that the heater does not heat up instantaneously and the time is not negligible, then the system must follow a second order system. In this system, the water temperature rises slowly at first, down here, and then gets faster after the heater is already reached its maximum temperature. Then, as the water temperature approaches the temperature of the heater, the rise of the temperature slows down again. The second aspect of the control system was that we looked at was the input parameters for the controller types. By looking at the open loop response without any feedback, we were able to determine what parameters we had to put into the controllers. We were then able to model the complete system, and Kevin will now talk about the LabVIEW interface that we use.
We decided to use LabVIEW as a program for interfacing and controlling the system, and this is one of our product panels. We thought that LabVIEW would do a good job of providing a visual environment for the students so they can better understand what's going on in the process of how we're controlling the situation. Here, providing graphs for them to acquire data, but also can write to a spreadsheet if they want the numbers a little more specific. Link to the computer and the LabVIEW is data acquisition board. LabVIEw does a good job of interfacing with inputs and outputs. And we had 2 thermocouples reading our temperature that we inputted on the panel as an analog input, and then digitally output on or off connected to a relay. We were able to control our heater. And since we couldn't have an analog signal to our heater, if we wanted to run the heater at 70% of the time, instead we turned it on for 70% of the time. So we get 70% of the power. Also with other front panels, we were able to simulate the project without actually running it to see, to compare how it actually runs versus how the transfer function of what we expect to happen. And we found that LabVIEW would be easy to modify for the conditions. Eric's going to talk about smart design.
Our STEM was built so that the experiments are simple and convenient for a student to do. The STEM is built with angular and frame constraints, and the duct is made at the top so that airflow through it will be smooth and continuous. The fan with sheet metal diffuser can be mounted or removed for different experiments. You may be able to see at the bottom of the stand. And brackets are made of metal to allow the canister to be placed in horizontal or vertical positions, which is at the top, and it is currently in the vertical position. The stand lets us easily change between different setups depending on the type of experiment that is going to be done. The fan will be in place if the forced convection experiment will be done. And for a free convection experiment, the fan will be removed. Different brackets can be placed at the top of the stand, depending if the experiment calls for the canister to be horizontal or vertical. The changes are fairly easy and should be simple for students to do. Now Ryan will tell what we can do.
This is a picture of our finished canister. The 2 blue wires are for thermocouples, and the black and gray wire. The gray wire is for our heater, and the black wire is for our pump. We put 2 thermocouples in the system, heater, and we placed one of the thermocouples in the center of the canister and one at the edge. This was done to provide greater versatility in the types of experiments the students could do. Also, the pump provided all circulation required to maintain water at a constant temperature by mixing it. The top and bottom of the canister were also insulated so that the equations the students could use for the system would be greatly simplified. Charles will now talk about the possible experiments in the system.
Our group wrote roughly a dozen different lab procedures to accompany the design, both in heat transfer and control systems. But since we don't have all night, I will just take you through one of the control systems experiments. This experiment compares the differences between proportional, integral, and derivative control. The students, as you saw the lab model, can switch the sliders and the knobs and stuff, and could set up the program for each type of system and observe the open loop response. From this data, they would then tune the system using the method from the text, such as Ziegler and Nicholson. After computing new values and putting them back in LabVIEW, they run it again. Then the students could compare the performance of each system before and after tuning and discuss the reports, the different costs and benefits for each type of control. Now Kevin will talk about the future additions to the center.
One of our requirements was that we wanted to be able to make the system easily add on to the future. And some of the possibilities we thought about were adding flow to the system, we originally thought of, and then we would have development controls involved in that, and that would also allow us to use this our device for possibly using experiments in thermal systems. We also thought about adding a second container around the original one that would allow us to produce a system where heat transfer to the outside is and finally we wanted to thought of possibly having to accommodate the system to include radiation heat transfer experiments. And any questions for any of this?
A very last comment, what kind of radiation experiments are you thinking of doing?
Primarily ones where radiation heaters would either be placed outside the canister or else radiation detectors would be placed around the container to determine the heat loss change when radiation is placed around the system, or determine the radiation that is lost from the existing system in addition to the convection heat loss.
Yes.
Will students next year be able to use that?
You'll have to talk to Professor DeBoer and Professor Brew on that. It should be operational.
Thank you very much, gentlemen.